Hello everyone. Let's talk about electricity and magnetism a little bit, some calculus treatment of it. Here we have, regarding my actual class at the school where I teach, we are going to talk about some things that we've already talked about and maybe didn't get a chance to talk about like we would like to talk about in a live setting. So some of this is being put on film. Some of this content has already been filmed elsewhere, if I remember correctly, having looked at some of the films, at least from the outside, looking at the title page. I think this has already been discussed, but that's all right. We can do it one more time for the road, talk about this a little bit. We're going to talk about, at least initially, before we get into Ohm's law and just talk about current resistance and potential difference, Ohm's law. Let's kind of go here and then build to Ohm's law just a little bit. Shouldn't take too long, should be pretty reasonable, guys. We're going to talk about current density. We're going to talk about current density, resistivity, and conductivity. Easy for me to say, right? Current density, resistivity, and conductivity. And we've already talked about live in the very recent class that we have currently going on, this particular situation when we talk about the current density and try to make some statements related to it. Our brilliant teaching assistant, Adam, brought up a great film to everyone that I think it's worth looking at. When we're talking about how the charges inside of a conductor, how they actually behave, that frequently doesn't get talked about too much. Oftentimes by the lecturer, like people like myself, and or some books. There's maybe more of an emphasis that can be placed on some of the things that our teaching assistant brought to our attention, which is very worthwhile. So what Adam had said to us was, okay, look, there's a particular film that talks about this. Push comes to shove when we're talking about how the electricity is manifested, how it flows through the wire, how it goes to a particular place to do something, to do some kind of work, goes into a particular kind of resistor called a light bulb to make the light bulb light. How's it going? Well, I kind of brought the scenario of like bumper cars. Why does this happen instantaneously? They all kind of bump into each other and that kind of makes it happen. That's actually not true. I was wrong. It's not a bad, I guess you could say, not a bad analogy to just be able to start things out and say, okay, well, let me just kind of, whatever it is, it's working. Now let me work with the mathematics pertaining to something like that. I guess that's arguable. The real big emphasis is something that I did say in lecture as well, but I don't think I emphasized it as much as I should have. It is the E field at the end of the day that's going to move everybody. Because the E field moves at the speed of light, it catches every electron inside of the wire. It catches every electron, every positively charged particle that flows, whatever you want to say. We work under the assumption that it is only positively charged particles that are flowing. We're saying, okay, there's some positively charged particles. They have the same charge as an electron. That's the charge of an electron in terms of magnitude. So that's the E. This is the number density, the number of positively charged particles per volume. And V sub D is the drift velocity going in the general direction of where the current is flowing. Well, like I said, the bumper car scenario, I guess, can kind of sort of be used to kind of placate us when we're trying to solve these problems and at least get down to the real mathematics of what's going on. But the real situation is, as I did say, it is the E field going at the speed of light that does hit everybody and will make everybody move. I didn't emphasize that as much as I should have, but yeah, the E field plays a big role. What they said in that film that Adam had brought to our attention, all the energy is in the fields, are in the fields, the E field in this case. B field as well, I think they mentioned in that film as well, but for our purposes, let's deal with the E field. The E field is making everybody move here. The bumper car scenario really isn't the best. It's the E field that's everywhere present in the wire that's going to move all of these. It's not going to move them that fast in a particular coordinated direction, for lack of a better way to say it. They're not moving that fast in a particular coordinated direction, but their random motion is amazingly, incredibly fast, according to that video that was sent, that our brilliant TA had sent to us. Talk to us about it. randomly, all those positively charged particles are moving on the order of 1 million meters per second. That's on the order of 1/300th the speed of light. That's crazy. 1 million meters per second is what they're randomly doing all over the place. Well, the fact that they're all random, they're not really accomplishing much as far as going into a particular direction until there's an E field applied throughout the wire. So the E field is what makes the whole thing happen, and it'll give it a drift velocity. Their random motion, however, is amazingly fast. As I said, on the order of 1 million meters per second. Randomly, everybody going everywhere in three-dimensional space. We coordinate some kind of motion with the drift velocity when the E field is applied, and it'll move everything. Okay, well, how fast will they move then? They're not going to move. Well, the coordinated motion, vector direction, V sub D, vector, it moving toward the right, because they're going to move this way in the direction of the E field, positively charged particles. Something on the order, I'm just going on memory here, something on the order of 0.1 millimeters per second. 0.1 millimeters per second. 0.1 millimeters per second moving to the right, whereas their random motion everywhere is on the order of a million. Is on the order of a million meters per second. So randomly, while this is going on, when there's no E field, they're moving in random directions at each one, on average, of about 1 million meters per second. When an E field is applied, they'll start moving in some sort of coordinated sense toward the right, and the random motion will remain. All the randomness that goes on will still remain at 1 million meters per second. But at the same time, there will also be a resultant vector associated with the drift velocity of 0.1 millimeters per second. Very slow on that order. Whereas randomly, while they're going slowly to the right at 0.1 millimeters per second, randomly in all directions, giving you a vector sum of 0, I guess you could say, the individual speeds on average are 1 million meters per second. But they don't add up to anything coordinated because it's all randomly all over the place. While that random motion is always taking place, regardless of the current that's going through here, that fast, the coordinated current is what we're looking at. And that's just 0.1 millimeters per second. And while that's doing, again, that randomness is going on, but as a vector sum, they don't add up to anything. Individually, 1 million meters per second while that's all going on. So that's pretty fascinating stuff. As we look at this in the book, in Dr. Deborah Katz's book, she takes this differential volume, and she says, look, there's a base area here. There's a base area here, A, or forgive me, a cross-sectional area. I guess you could say a base area. Cross-sectional area A. This is also equal to the cross-sectional area A. This is also equal to the cross-sectional area A. Let's just keep it like that. There is A times dx. That's a volume called D capital V. Also A moving through dx. A volume D capital V as well. Okay. Well, they want us to kind of draw a conclusion related to this thing called the current density, J vector. I'm writing this in terms of vectors at the end just to kind of give us a gut feeling. Since we know what direction things are generally moving, even though all that randomness remains forever, there's a coordinated movement at the same time called the drift velocity. We can just write it like this if we know where it's going, and we don't have to really put the vector notation on there. So what are they saying on some of these for us to actually make some sense on it? They're saying basically, you guys, as we look at this, and again, I did this in class and lecture, but I want to kind of just take this one more time, kind of build on it, and then get from the current density that I'm talking about, I like to talk about the resistivity. and I'd like to talk about the conductivity. They are inverses of one another. If something has high resistivity, it doesn't want electricity to flow that easily. If it has high resistivity, that means it has low conductivity. It can't flow that easily. If it has low resistivity, then it does conduct very well and it has high conductivity. We'll cross the bridges as we need to cross them, I guess you could say. They are making a statement, and let us just make a couple statements as well. They're saying J is I over A, is the amount of current, and they put 3 lines right here, meaning, kind of a definition here. I over A. I is basically, charge passing a particular cross-sectional area A, charge passing a particular cross-sectional area A in a time t. A little more rigorous look at that would be dq dt. And this is more of a gut feeling look at it, but this is more the rigorous look at it with some calculus base to it. We got this right here as well. They talk about, they talk about the number, they say like the number density. They use a small, and this is just their definition. Obviously, words can mean different things in different contexts. You got to define what you're talking about, then be faithful to the words that are being spoken, I guess you could say. Faithful to the definitions. With that in mind, N is, number of charge carriers per volume, per unit volume. And capital N is just the total, independent of volume, total number of charge carriers. Like I said, we already did this in class. Those of you who missed it, you got an opportunity to look at it again here. There's other places in which this gets talked about, depending on the film and stuff, and in the context in which we're talking about it. This is number of charge carriers, total number of charge carriers. Delta T is, well, there's a lot. How much do we want to talk about this thing? I guess in a time delta T, you're going to go from one cross-sectional area to another. So you're going to cover delta X between the distance that you're going to cover between one place, between one cross-sectional area and another. You can go right here. Now, guys, this wire itself is a cross-sectional area of a wire. Wire can be very long. When this stuff moves out, other ones move in. When these move out, these guys move in. When it moves out from here, so from way back here, everybody's eventually going to cross over this way, and this is what it looks at any particular snapshot. So everybody's crossing over a particular volume. Everyone is crossing over a particular cross-sectional area. You're covering delta X in a time delta T. Well, that's interesting. Then V sub D, in terms of magnitude, is going to be the distance delta X that you cover over a time delta T. Again, and this gets explained in a non-calculus background and non-calculus classes in different ways, folks. But you're looking at a situation like this. They also talk about E right here, and that is the charge on the positively charged carrier. The amount of charge, amount. So amount of charge on one, so I'll write it here. On each one, on one positively charged carrier. If it was an electron, it'd be negative 1.6 times 10 to the negative 19 coulombs. If it was a positively charged charge carrier that had the same charge as the electron in magnitude, but it was positively charged, it would not be negative 1.6 times 10 to the negative 19 coulombs, but it'd be positive 1.6 times 10 to the negative 19 coulombs. So that's where they're coming here. This, generically, you could put a different symbol here if it was a different charge in any sort of hypothetically positively charged character, when you're on any positively charged item that you're talking about. So okay, guys. I mean, so this is kind of like the game they're playing here, and how are we drawing these conclusions, or are basically identical? This is straight out vectors. This is without vectors. If we know what direction everything's going, and we can use this to kind of look at later on. When we get to here, we're talking about the current density. Well, we already know the current density, at least in terms of a definition, is this, but we'd like to relate it in terms of that all-important E field. Our gut tells us the stronger the E field, the bigger the value, the bigger the magnitude of the E field, the more current's going to take place. The more current is going to penetrate past any particular cross-sectional area. When that's the case, the more current getting through any particular cross-sectional area on this wire, the more current, I over A is going to be a bigger answer. So the bigger the E field, the bigger the current. Smaller the E field, smaller the current. Okay. Kind of goes hand in hand what I was trying to say earlier. So we have a situation like this. Okay. So if that's the case, let's actually see where it derives from here, and then we'll put some other stuff up here. They play the game here. Like I said, now everybody's getting replaced. Even during this quote-unquote order, or even with this orderly progression to the right of current, forgive me, of current's okay, that's okay, of charges per unit time passing a particular cross-sectional area, all that current passing, all that charge passing each cross-sectional area, all that current passing that particular cross-sectional area. In other words, all that charge per unit time passing a particular cross-sectional area in a somewhat orderly fashion at a speed of v sub drift velocity, v sub d. Yeah, while that's going on, there's this tremendous randomness as well in all directions, on average, moving, all the charges moving in random directions, each one on average somewhere on the order of 1 million meters per second. Because it's all random, it doesn't really generate anything to the right until there's an E field, while that randomness in the charges continues with the great speed, but randomly directed. The great speed of 1 million meters per second, randomly directed, remains, E field or not. The E field just takes that, while all this random stuff is going on, it's moving them while they continue their randomness at 1 million meters per second, but they're going this way, which, because of the E field, goes throughout the current. There's a general movement, in this case to the right, and we're able to actually power a light bulb. The randomness didn't really get us anywhere because it's indeed random. It's just going everywhere. We gave it some order and we allowed the randomness to continue. That order is nowhere near, that V sub d is going to be nowhere near 1 million meters per second to the right. It's just going to be whatever V sub d is. We can find out what that is. I mean, we've done some of the problems to actually find out what that speed is, and it's not that much. It's on the order of 0.1 millimeters per second, as we've said numerous times by now. So you're looking at all this. Let's remember it. Let me get this out of there. Let me leave this. And, let's just kick this around just a little bit and then see some other stuff that we can say. Okay, well, how's this whole thing playing out? Well, we know, let me kind of lose the vector notation a little bit and just kind of draw the conclusion more looking like this, but in reality, this is what's going on in the strictest sense. Every time, if all of this right here, that whole volume ends up over here, and then somewhere over here, that same volume, same amount of charged particles also ends up here again, only to end up over here and have all these that are going to be over here end up over there, and so on and so forth. If every time this volume, a volume like this, is going to cross over to here and this is going to cross over to there because of the E field, kind of making the whole thing happen. All the energy is in that E field. So you look at it and you say, okay, what's going on here? Well, there's a volume of what's going on. They go about it, a little differently than maybe I need to go about it. We'll see. We'll kind of talk about it, I guess you could say. We could say that the differential change in volume, this whole amount of volume of charged particles, making it to here in time delta t, this volume delta V of charged particles making it to here in time delta t, moving with drift velocity, not a very impressive drift velocity, but it gets the job done apparently. And we got something like this. That big amount of volume is the area moved through a distance dx. That change in volume is area times dx dt times dt. Well, wait a minute. The dx dt, at the end of all that, the dx dt was v sub d. This is dt, and that is the change in volume that is occurring. Okay, that's the amount of change in volume that's happening here. I wonder, in that change in volume, how many actual particles are being, I'm taking this a little differently than the way Dr. Katz did. It is essentially the exact same argument, you guys. That's for sure. Let's talk a little bit. We can say that. Let me kind of, again, I'm going a little bit different the way. It's exactly the same argument, but let's see what we can say here. I'd like to find what J is, and J is I over A, as I remember. So I kind of got that in the back of my mind. I'm shooting for J being I over A, and an I is dq dt over A, and or Q over T. We'll say dq dt. It's better for us, I think, right now. But we got that in the kind of the back of our mind when we're looking at this thing. So kind of just as we're getting here, let's indeed get there. I'll tell you what, is it true that the total number of particles that are crossing over, capital N, that's equal to the charge density, number of particles per unit volume, times the volume? Yeah, well, those number of particles is the charge density times the unit volume, which is V sub d dt, to get there. Okay, I can buy that. And to find out the total amount of charge, each one of these n particles has a charge E on it. So you could put, like, I hope I have room here. Let me just see how this is going to work out. Every time I erase these, it's almost not as visible. So hopefully this looks okay for you guys. Each one of these capital N number of particles has a charge E to it. So put an E there. That's the total amount of charge. That's the total amount of charge. So what you got here is total amount of charge, which is N, E times small n, E times small n, or small n times E, V sub d dt, that's the total amount of charge. How do you want to say it? I mean, probably want to follow Dr. Katz pretty closely on this one. We'll say that's dq. It's the total amount of charge. Tell you what, if you divide by, you got this right here. If you divide by dt on each side, hey, you got I. You got I. You got I equals, that's this guy, that's I, NE V sub D. Let me didn't multiply it by A. Let me see here. Something happened here, guys. I got to make sure. Yes, this is a problem here. Let me please. I have to come back. Let me just come back. There's something wrong here with that. My fault. What is delta V? Okay, that was my carelessness. Delta V is A dx. Delta V is A dx dt, that's A dx. A dx is A delta x dt. Delta big V is A V sub d dt. I did not put the A in there, guys, so forgive me. Let's, probably, if you're angry with me, I don't blame you. Let's remember that then. So if we're going to say regarding this, if this is the way it's looking, let's try to find out the total amount of charge that would be present given what we got here. A way you could say that is if you took the number density, if you took the charge density, which is number of charges per unit volume, and you multiplied it, number of charges per unit volume, and you multiplied it by the volume, you'd have the number of charges. Multiply it by the charge on each charge carrier, and you're going to have the total charge that's present in this area, in this particular place right here, in this red area right here, or this, this area right here, or this area right here, or the area right, in this volume, or in that volume, or any other volume, you can look at something looking like that. And, where does that come from? Well, that's pretty interesting. You could say that the way that whole argument, I guess, proceeds, I mean, just to say it, if there's a total of capital N charge carriers, and each one has a charge E, that's the total charge that is present in that volume. Well, yeah, big N is small n delta V times E. And that's the charge, so E is the charge per carrier. There's capital N number of carriers in a particular volume, delta V. If the charge density is small n times delta V is, small n times delta V is going to be capital N, total number of charges. If that's the total number of charges, and yeah, I guess you could say that. I mean, that's total number of charges present, so dq is En delta V. If you divide it by delta T, you've got this. If you divide it by that whole, that's I. And if you divide all of that by A, you basically got I over A. That's what J is. And that's this right here. That's En Now this doesn't do me a heck of a lot of good, but let's just write it down for the sake of the mathematics, if for no other reason. You're looking at something like this. Yeah, this is true, but is there a more compact way to go about it? Yeah, there certainly is. What happens is, again, we're shooting for this as the goal here and try to find an answer. Well, I'll tell you what I'm going to do. There's an amount of dq. dq is all of this. dq is all of this separately. This is dq, over here in the same differential volume, delta big V, there's also a dq. In the same differential volume, delta big V, this will be a dq over here, same differential volume, delta big V, there will be a dq over there as well. So that's what we're talking about. Okay. Well, yeah, I think it makes sense. I mean, if I can take the number of charges per unit volume and multiply it by a particular volume, I have the number of, then this right here gives me the number of charges. The number of charges times the charge on each charge gives me the total amount of charge. That's dq. And dq, like I said, is right here or right here, as long as it's the same differential volume, or anywhere else, as long as it's the same differential volume with the E field being applied. Then you say, okay, fine. Are you okay with dq being En delta V? Delta V is area times delta X. Okay, that's true. That's true. Yeah, and area times delta X is this. That's dV. Well, yeah, I know. The delta X, you guys, is V sub D times dt. V sub D times dt, that right there is delta X, just right here. So that was kind of something I missed earlier. Okay, so that right there is delta X. Every time I see a delta X, I can deal with the fact that indeed whatever it is. I mean, delta X, I put it on somewhere. I think I put it on somewhere, and then I ended up erasing it. We basically said, guys, the delta X is going to be V sub D times dt. I think we did that way earlier, but just for I guess completeness, delta X equals V sub D dt. That's delta X, and that's going to be V sub D dt. The delta X is V sub D dt. So what we have here is, guys, okay, I forgot you guys have the feature where you can go back with the film. So you should be all right. Everything we said is okay. After I just had to correct myself, my fault. But earlier, dq is going to be En A, and dx is V sub D dt. You want to divide that by dt to get the current I. That's the current I. When you divide it by dt, see, before it was just dt, before it was just dq equals ENA V sub D dt. Divide by dt on each side. I equals ENA V sub D. Divide by area. Yeah, what I wrote earlier is fine. It's an awkward thing. You can't. Perhaps you can use it in some context, but this is so much more abbreviated and yet very accurate at the same time. Divide by A on each side. J is I over A. It's En V sub D. Again, we already did that, folks, in lecture. J is En V sub D. Well, that's going to help us out. En V sub D, the Katz book writes it Ne V sub D. That doesn't matter. I mean, the commutative property is alive and well. En V sub D is the same as Ne V sub D, and we have that right over here. Same thing. All right. Going with that, I mean, you only have so much time looking at some of this stuff, guys, obviously, but when you want to look at resistivity and conductivity, maybe there's an analogy here that can be seen. Now, they throw some, in some of the explanations in the Katz book, and the Katz book is a great book. I mean, I think it's an excellent book. I've grown to appreciate it very, very significantly, very, very much. It's an excellent book. We can say a few things. Well, I'm going to leave this conclusion, because we believe this conclusion to be true. We derived it, again. This is in other places too, guys. I think there's other videos where I've actually gone into this at least once before this, and also live we talk about this stuff. So we look at this, we have this. Let's see what we can say. Using this, can we learn something about the E field, the electric field? We talked about how important it was, how it gets underestimated sometimes, including by people like myself. So, I mean, we talked about the E field, how important it is. And is there a relationship between the E field and the amount of current that flows? And again, the current density, I over A, is, for a given constant area. And that's not guaranteed that the area is going to be constant in a particular scenario. The area can vary, and that's something you have to keep in mind. But let's just hypothetically keep the area constant. If J is going to get bigger, then I's got to be bigger. If J is going to get smaller, then I has to get smaller, if the area is constant. Now, there's other scenarios where maybe the area is not going to be constant, and we have to talk about that. But the big thing is, generally speaking, just to kind of play the game here, let's say you're playing with an area that's kind of staying constant, hypothetically, at least for one circumstance. The current gets bigger, or the current gets smaller, or the current stays the same. In what circumstances does that hold? Well, if all other circumstances are the same and the E field stays the same strength, the current is going to be the same, steady, not bigger, not smaller, whatever it is. If you make the E field stronger, the current will be more. If you make the E field weaker, the current will be less. So, and they kind of go into this, they use kind of negative numbers in Dr. Katz's book and stuff. She does brilliant discussions. Let me not go for the negative numbers as much. Let me just kind of look at it and say, well, is there a way we can look at the E field based on things that we have talked about and kind of figure out what we can say there? Well, the drift velocity is high. If the drift velocity is higher, when there is a longer average time between collisions, the higher drift velocity between collisions means a higher current density. So if the drift velocity between any kind of collisions or anything else, guys, if the drift velocity is bigger, it makes sense. I mean, if this stuff's going to drift at a faster speed, if it's going to vacate this volume and find itself over here, only to be replaced by the same amount of particles on average, same amount of charge density on average, coming into the same volume in a shorter period of time. If all this movement is taking place, if all this volume is being occupied, all this volume of charge is being moved to the next volume of charge over to the right, only to be replaced by other amount of charge from somewhere else coming in there, and it's happening in a shorter period of time, that means that the drift velocity, if it's a shorter period of time for all that to happen, the drift velocity is greater. And that's indicative of more charge passing through a cross-sectional area in a given unit of time. If more charge is passing through a cross-sectional area in a given unit of time, it's more current. And vice versa. If less charge is passing through a particular cross-sectional area in a given period of time, there's less current. Okay, that's kind of what they're saying here. kind of carefully look at this, guys. Doing it a little bit on the fly here, but I just wanted you guys to get exposure to some of what's going on here. We know some things. I mean, we know some things. Let's talk about some things. Let me go a little bit differently than where, let's say, maybe Dr. Katz is doing on something like this. Let me at least say, and use some of her terminology as well, but not use maybe the negatives as much. Let's say the charge on each individual particle, is E. The charge on each individual particle is E. You guys remember that the force experienced by a charged particle of charge Q in an E field E, Q times E is the force. Now, so the force experienced when the charge is E, the charge Q happens to be the value E, small e times big E will tell me the force that's being experienced. If I divide that, and I'm going a little different than what Dr. Katz is doing here, guys. If I divide that by and I don't want I'm using some of the terminology, and then but maybe the language I'm using is going to be a little different. If I divide by the mass of the charged particle with charge E, if it's the electron that we're talking about, it's a different charge than the charge. The charge on the electron is the same as the charge on the proton, but the proton is more than 1,800 times the mass of an electron. I don't want to go there. Let's just say, look, there's a charge E of some particle. I'm not going to be too specific. There's a charge E on some particle, and it's the mass of the particle with a charge E. We'll say it's a positively charged particle. They're kind of not doing that in the Katz book. They are and they are not in a sense. But let me kind of just do a little bit of my own thing on this. We said F is equal to Q times E. F equals Q times E. Therefore, if F equals Q times E, F is equal to small e times big E if Q is equal to small e. Sounds good to me. If I divide by m on each side, force divided by mass is acceleration. Don't concern yourself too much with what kind of particle I'm talking about. It is some particle. It's got a charge E. It's positively charged. And that's good enough for us right now. So you're saying, okay, force divided by mass is acceleration. Then they say, okay, there's kind of a way we can get out of this. We can say that, how fast is this thing going between collisions? So they're saying they're going a little different on this whole thing here, guys. But we're not gonna really do that. We're gonna say they got this thing they call. For some reason, I can't even find it here for some reason. Okay. There is one second here, guys. Longer average time between. The time between collisions. So, is it on the other page? And I just happened to miss it. Let me just see here. Yeah, they call it the mean free time. TMF, the mean free time, the average, they do different things here. The average time between collisions is called the mean free time. To find the average y component, okay, they go with the analogy of gravitational field and relate it to an electric field. I'm kind of trying to bypass that, and I'm getting caught in this a little bit, but I'll try not to. The mean free time is the distance between collisions, how it can freely move and how fast it can go between any kind of collision for any particular particle. Well, you can kind of say this. If this is the acceleration that it's undergoing, what kind of drift speed they're saying? They're kind of making a, the drift velocity is higher when there is a longer average time between collisions. The higher drift velocity, longer time between collisions means a higher current density. So J equals NE V sub D, and that's all that right there that we're going to talk about in a second. So they're saying that, well, V sub D itself, and I'm trying to kind of modify this a little bit, guys. Small e big E over ME equals times TMF will give me V sub D. So we're saying you're going to reach a drift velocity in a particular direction coordinated by the, and I'm bypassing some stuff in Dr. Katz's discussion. Hopefully that's going to be okay. It's going to be acceleration times, okay, so that's, as we said here, guys, the mean free time before any collision happens. The more time you got for this not to happen, well, how does that help? Well, I guess if you got a real big cross-sectional area, could be a lot less chance that could happen, right? That's maybe why the resistivity itself is inversely related. How resistive is a particular conductor? How much resistance can happen? Well, it's got less resistance, all other things equal. There's a lot of area, a lot of cross-sectional area. But if it's long, then it's going to tend to have more resistance, more resistivity. So directly proportional to length, inversely proportional to area. So there could be a connection here. For right now, let's just stay with this. V sub d is A, this right here. Well, if that's the case and this is A, then we're talking about V sub d. The A is EE over ME times the time. To make this happen. Okay, yeah, I mean we can argue that. We can say a lot of stuff related to this, guys. So any V sub d. So if they're saying if kind of sort of we're believing this, I guess it makes sense that if in all this randomization we can set this thing up that V sub d is going to be a big number. Well, how does V sub d become a big number? Well, the best way for it to have a big number is for it to have a good acceleration. The thing that's going to control the acceleration, all of the things equal, if this is a charge, whatever it is, well, you know, E, whatever, but this is a charge, this is the mass, if that remains the same, if E is bigger, there's more acceleration. With a given acceleration, you guys, for the particular mean time under consideration between collisions, if the acceleration is really big, you're going to at least be reaching a big average drift velocity, so they're tending to get out of any particular volume. They're tending to get out of any particular volume and going to the next equally sized volumes and being replaced by things from other volumes that are equally sized. They're just coming around. Everybody's getting out of there a lot faster. That's a bigger current. So it would make sense that there's going to be bigger current given that there's a big acceleration for any sort of mean time, for any mean free time between collisions. Well, how's that going to happen? Well, let's just keep that constant. If this is big, V sub d is going to be big if A is big. The only thing that's going to make A big, if small e and ME are constant, the only thing that's going to make that happen, here's our friend again, the E field. The E field's going to make A happen really much. A is going to be really big if E is really big, and if A is really big, V sub d is really big. If V sub d is really big, this goes to here, that goes to there goes to over here, whatever, but it all happens a lot faster. And that's because of the E field. So they look at this and they say, okay, if that's what you're going to say, and the acceleration we just talked about with the whole song and dance, F equals QE, Q was equal to E, Q was equal to small e rather, there's the big E, and you got it. I mean, you know, Q times big E gives you F. Q is the small e divided by ME on each side. We're doing the whole song and dance. For any given TMF that we're talking about, guys, whatever's going to determine this, let's say this doesn't change at all. If this just changes, even if that doesn't change, if this changes for the bigger, V sub d is going to be bigger, and there's going to be a higher current. It's going to be a bigger I. Why? Because the volumes are clearing out a lot faster. That's when we're going to look at it. So when we get to here, you could say, okay, well, wait a minute. Didn't they say that J is this whole song and dance? J is NE V sub D. And yeah, well, I mean, let's talk about it. So what we have here is, at this point, let me stay relatively close to Dr. Katz on that. NE V sub D, here's V sub D. There's a relatively big song and dance here, but let's see where it's going to go. We got N, we got E, and we got a lot. We've got ME, T, let's see where they put the TMF. Yeah, they put in the same place there. Okay. Okay. Okay, it's the question of how I want to set this thing up and how I want to end the thing. We are looking at it right, and they didn't really say anything much about the TMF. They're just saying, okay, things can happen. I mean, there's an average time between collisions. It's called the mean free time. Find the average y component of velocity, replace t with the TMF, which is like our version of some t under consideration. In very, very many circumstances, the TMF is going to be something that's, if very many parameters are equal, there shouldn't be much of a difference in TMF. The thing that's going to change things quite a bit is the fact that the thing is accelerating more with a greater E field. That's what I see here. I could easily be wrong, but I don't see where it'd be something else. Perhaps there's some other play that goes on here with the TMF. But basically, guys, all other things equal, the TMF should be for a particular circumstance, whatever it may be. What changes the circumstances here is how much travel is taking place before the collision. The collisions may be taking place on average the same amount of mean free time between collisions. Yeah, maybe. Yeah, the thing is, it's traveling a lot further during that time before the collisions happen. It may be happening the same amount of time, but the collisions are, they're taking place the same time, but everybody has moved a lot further because the E field is stronger. That's the way I interpret that. I don't see anything different on that. It's certainly not a bad interpretation for at least being able to do these problems, you guys. So as you look at this, let me just try to put this somewhere the way they're trying to go with this. Yeah, I think they kind of just stay there, you guys. They don't. I think they just gave an analogy here. Right. I mean, they're basically covering. The way we don't need to go there too much, guys. The big thing here is we said E plays a pivotal role in very much of what goes on. So if that's going to be the case, let's deal with this. As long as we know the direction, I've kind of like negated. I've not talked about too much of a vector quantity. Everybody's just going to the right. Here's small e. Here's small e. That's NE squared. Here is, so here's, right, so here we got small n, small e, small e, small n, small e squared, over ME, and they got TMF right here. And let's see here. Yeah, this is a big thing, guys. Yeah, we're forgetting one big thing. This guy comes out here. Well, they kind of said this. Now imagine putting two different conducting materials between the plates of a capacitor. The electric field in each conductor is the same, but the current density in each conductor depends on the proportionality constant, what I got right here. The conductor with the longer average time between collisions and the higher density of conducting electrons will be the better conductor and have the higher current density. This constant of proportionality is the conductivity of the material. Okay. Basically, guys, to make a long story short, if you're given a particular E field, if you're given a particular E field, what's going to make J, I over A, the biggest answer possible? A huge density of charges per unit volume, a lot of charge per carrier to the square of it, not much mass. The smaller mass you got, the better off it's going to be. And the more time between collisions will also play in your favor to make this a really big number. And if it's a big number and you're multiplying it by E, J is going to be relatively big for any given E. So the way they go there, guys, I mean, we said a couple things. Let me kind of get rid of a couple things here. Now I said, I mean, the scenario here, if we're talking about a given temperature, a given geometric configuration for a conductor, a given temperature, everything the same, all things the same cross-sectional area for the given geometric configuration, all things equal, my take on this is, and I don't know. There's no real explanation here, so I'm going to admit some ignorance on this. But, the TMF is a situation where it doesn't look like there's going to be much of a difference in the TMF, all circumstances considered, but the thing that really makes it happen, and of course I didn't erase it actually. If the acceleration is really big, that's what's going to make it. That's what's going to make it happen. You're going to have a lot of drift velocity if you've got a given amount of time, which may or may not vary. I'm going to confess my ignorance on this one, which may or may not vary in a particular circumstance. But if, hypothetically speaking, if the TMF is the same in all circumstances for a given circumstance, this is going to really make it happen for V sub D to be really big, which is going to get a lot more charges moving out of a given cross-sectional, through a given cross-sectional area from a particular differential volume. There's going to be a lot more charges leaving every differential volume if V sub D is big. V sub D is big happens for a given, let's just put it that way, for a given TMF, if A is really large for a given TMF, the V sub D gets big, and there are a lot of charges vacating any given differential volume going to another differential volume with the charges that were there before, where the charges have come into another place, those charges that were there before are also moving out at the same rate, and it is a high rate because V sub D is big when A is big. When does A become big? Well, A becomes big when it's force divided by a mass, which is QE divided by a mass. And yeah, if this is a constant, the bigger the E field, the bigger the acceleration. So it depends on E for you to get it to go. What does that mean? Our gut tells us that if E is really big, there's a lot more charges going through a particular cross-sectional area. What is that? That means there's a lot of current going through a particular cross-sectional area. That means there's a lot of current density if E is really big, generally speaking. This right here depends upon circumstances. How much charge density is there? What are the charges per charge carrier? What is the charge density of the charge carrier? What are the masses of each charge carrier? And how much time is there between collisions? There's a lot of time between collisions. It's not very massive. If this is big, and this is big makes all of this big, small makes all of this big, and a lot of charge density and a lot of charge also makes all of this big. So small n, small e squared, TMF, if they're big, it's going to be a big answer. ME, if it's small, it's going to be a big answer. And whatever the circumstances are here, they call this the conductivity. This, If this is big, it's easier for conduction to be taking place if all of these occur. That's probably the biggest takeaway here. They don't go, like I said, I didn't look very closely at the gravitational analogy here, but they're saying, they didn't say how, how that's all going to happen. They just didn't go there, guys. They're saying for the initial speed, they're saying TMF. I think they kind of let that go, and they said, okay, well, whatever that may happen to be, just know something for sure, and that's really important. There's a lot of time between collisions, and there's a lot of charge per charge carrier, and there's a lot of charge density, charges per unit volume. If all of this is a big answer, divided by each particle that carries charge not being very massive, well, it's inversely proportional to mass and directly proportional to these. This is huge. And that's they call it, well, that's going to help the conductivity. So what happens is, it is indicative of something conducting very well. So they say the way this would work is you'd say, okay, the conductivity would be NE squared ME I just want to write it just like Dr. Katz wrote it, or close to it. The TMF is on top, not on the bottom. Let me just see how they wrote that. I want to make sure. Yeah, they kind of put it in the middle. NE squared over ME, TMF, that's sigma. We'll define it like this. If this is a big answer, this thing really wants to conduct. It'll conduct really well. What does that mean? Well, they get pretty crazy about it. They say, okay, well, didn't we say this whole song and dance right here? Okay, and this is, like I said, on top. This whole song and dance right here is sigma E vector. And that's what sigma was, and that's all. This is exactly what we wrote right here. Just we said, okay, sigma is equal to that. That's the conductivity. Well, if this is a really big number, yeah, that's a lot of conductivity. Big number times big number. For a given circumstance, you could have an E that's constant, and if the conductivity is not that good, there's not going to be a lot of current density. You could have an E that's, like I said, a big number, but if sigma is a small answer, J is going to be a small answer, the current density. If E's a big number and sigma's a big number, yeah, then J will be big. It won't be small. So it's about the conductivity. They said this thing called the resistivity is 1 over sigma. So what does that mean? Well, that means this. I mean, whenever this is a really big number, 1 over sigma is a really small number. Whenever this is a really small number, 1 over sigma is a really big number. If this is a small number, things don't move very well if it's a small number. 1 over a small number is a big answer. That means there's a lot of resistance, a lot of tendency for there to be a resistance to the flow of electricity. If this is a big number, then 1 over a big number is small. That's a small answer. There's not a lot of resistance to the flow of electricity. So they're reciprocals of one another. That's kind of the way to look at it. Sigma is conductivity. Rho is resistivity. And they go there. I mean, they go rho is equal to, so they play that. And let me see. So they basically, I mean, I guess there's a lot that can be said here. I mean, you could say, go back to vectors if you wish. I mean, so they didn't go really into the TMF too much. You got this, which is the same as 1 over rho E vector. So I guess what you can have here is E vector, the amount of E field is rho times J vector. rho times j vector, and here j vector is sigma times E vector. So these two are of interest. The way they kind of wrote this thing out is they say, okay, on the other side of that, you can write rho is the reciprocal of 1 over sigma, which is me n E squared. Here I'm going to put the TMF right on the bottom because it belongs on the bottom. Here it's on top, so here it's going to be on the bottom. Absolutely. Equals this. They didn't put the 3 bars on this. I'm not sure I want to nickel and dime all of this, guys, but okay. Let's do it anyway. So we got this. This ME is M subscript E. Be careful. And we got that. So we're looking at that. So what we're saying is true here. How this, the mean free time that this is all going on, the T sub MF, they didn't go into great detail on that to my knowledge. Let me look at that again, guys. I don't want to kind of leave you. If I do this, I'll add an addendum to this particular video, and we'll figure it out. I don't think it was there. Yeah, they kind of gave an analogy that's a very good analogy. Yeah, they didn't unless I'm missing something here, folks. In the which I could be, but I don't think that I am. I'm looking at the Katz book. They're not really giving find the average y component here. They're doing an analogy here with gravity. Replace t with the mean free time. They're saying now imagine putting 2 different conducting materials between the plates of a conductor. The electric field in each conductor is the same, but the current density in each conductor depends on the proportionality constant. We already said that anyway. We agree with that. The conductor with the longer average time between collisions and the greater density of conductors will be the better conductor and have the higher current density. We already said that, absolutely, unequivocally we've said that. This constant of proportionality is the conductivity sigma of the material. So they didn't go into any specific, so it's fine. I think we're safe, I guess, to say, well, let's not talk about the TMF as far as that. It exists. There's a mean free time between collisions. There are probably very many things that come into play here, apparently none of which are discussed here. We just know the reality of it, that there is a total mean free time between here, and we got all this happening. That's it. I just thought, again, I did not have the time to do that last time we were in lecture, guys, so I figured I'd go into it now. We did say some other stuff. And again, it just made a lot of it just made a lot of sense regarding some of what can happen here, guys. We talked about some different matters of interest, and we already did it. We already talked about very briefly toward the end. We had to kind of rush it a little bit, but the power in a circuit and how things play out. Let's talk about that very briefly right now, and then we'll leave it at that. All right, let me just pause this for a second and set up something else really quickly here. And again, when we get together, guys, we can talk more about this. So thank you for your time. Just give me, again, it's probably about 5 minutes more beyond this. Let me just put this on pause for a second and find out what we're going to do. Okay, everyone, welcome back. Let me just quickly do something we had done last time, kind of real quickly. I mean, we could talk more about it in person. there's always a lot more to talk about than there's time to talk about it, just about always. Again, having come back to what we were talking about earlier, resistivity and conductivity. We talked about conductivity first. We talked about conductivity, and we also talked about resistivity. And conductivity and resistivity are inverses of are multiplicative inverses of one another. Conductivity and resistivity are reciprocals of one another. They don't necessarily tell you how, how was this E field generated? Why is it that the TMF, the mean free time between collisions, is what it is, very big or very small in a particular circumstance? Small n, the number density, the number of charged carriers per unit volume, E, the charge of the particle, the mass of the particle. I mean, there's a lot of things that come into play. Let's just know if whatever reality exists and whatever parameters are given to us specifically, when they tell us what small n is, what they tell us what small e is, what they tell us what m sub e is, the mass of the charged carrier, when they tell us what TMF is, the mean free time between collisions, when they tell us all this stuff, we can draw the conclusions related to sigma and rho being reciprocals of one another. Conductivity and resistivity, the quantities associated with each, are reciprocals of one another. We've already discussed that. And that's kind of the main thing, the big thing to talk about. Just to briefly hit this and kind of leave it, and we did it last time, we obviously talked about, force being QE, and we talked about work being Q times delta V or V. We said it depends where you're going to go, guys. V means delta V, and delta V means V within particular contexts if we can read within the context of what they're talking about, if we're faithful to the context of what's being said. Makes sense to me. I mean, if you go here and you divide by T on each side, Q divided by T is I, this is V, W divided by T is power. Okay. If they tell us that the amount of current that flows is directly proportional to the potential difference that is occurring to make the flow of current possible, there's a large potential difference and a small resistance, I is directly proportional, current is directly proportional to potential difference and inversely proportional to resistance. V equals IR. We're coming here. Well, if V equals IR, put V equals IR here, and the mathematics gives you this. That's some of the stuff that gets talked about that we can, that we can look at what's happening here. Said some other stuff. Let me just quickly. I'm not going to. I mean, a lot of this we're going to do in person anyway. We just got to be careful a little bit, I guess, like anything else. Yeah, by the way, if I is equal to V over R, then we got I is V over R, the quantity squared. Forgive me, V over, this is wrong. Forgive me. If we're going to, guys, just to be safe, let me not let this happen again. We agree with this conclusion right here. If they tell us that indeed a large amount of voltage, a large amount of potential difference, and not much resistance, directly proportional to potential difference and inversely proportional to resistance is the current. Current is directly proportional to potential difference and inversely proportional to resistance. Directly proportional to V, inversely proportional to R, comes out to here. Not a problem here. If we're going to do that, let me just, so we can play it safe here. V is IR if the power is IV. Now, there was nothing wrong with what we did over there. Good intuitive feel for that. Let's put V right here. Let's put V equals IR right here, and then you won't make the mistake that I made. Luckily, I caught it, and we're correcting it. We got this. So we got P is I squared R, P is IV, and by the way, if I is V over R, if I is V over R, you go I squared R, P is going to be equal to V squared over R squared times R. The R's cancel. P equals V squared over R. And again, we'll get into this in more detail, guys. Please forgive the earlier misstep on that, but here we are. I mean, you got this, and we can figure that out. It is a big thing to be aware of this. If you've got a lot of potential difference and there's not much resistance, there's going to be a lot of current. If there's not a lot of potential difference but a big resistance, there's not going to be a lot of current. There's a lot of potential difference going on. Well, that facilitates a lot of current. If there's not a lot of resistance, that even more facilitates a lot of current. I is directly proportional to V and inversely proportional to R. Play with this and you come out to here as well. So good stuff here. And we're reaching this, how we did some of the derivations here. We're dealing with that. All right, guys. Thank you so much for your time. We'll talk again soon. Take care.